In this lecture, we're going to take what we know about redox reactions and apply it to electrochemistry. So let's dive in. Let's start with a spontaneous redox reaction that occurs. If I take a copper wire and I place it in a solution of silver nitrate, what will happen over time right away is the solution will start to turn blue, and there will be this kind of silvery, this like gray colored precipitate that forms, which you can see in our picture right here. And so this is our kind of before and after. And this is a reaction where the copper wire right here is forming copper nitrate. And so that blue color you see in the solution is coming from those copper +2 ions that have formed. And then we have our silver nitrate, which you can't see in this picture because it's in solution inside the test tube, is forming silver solid, which is that gray, silvery, because it's silver, or precipitate or solid that forms within our test tube. And what's happening here is we're seeing that copper being oxidized to copper +2, and our silver plus being reduced to silver metal. And when these two come together, with the copper and the silver nitrate come into contact with one another, this happens spontaneously. So we can take advantage of these spontaneous redox reactions to create voltaic cells, which will allow electrical current to pass through a wire. Let's take a look at another redox reaction, zinc and copper sulfate. And what we have here is we have zinc, which is these strips of metal you can see right here. This is another before and after. Our copper sulfate is this blue solution from the copper +2 ions. And when we start with this blue solution and this silver zinc metal inside the solution, zinc that looks silvery, the color, then we see over time the solution becomes less blue. And we see this solid appear on our zinc metal. And that's really copper that's forming right there. And our solution, our copper sulfate, is decreasing in solution, and we're replacing that with zinc ions instead, which are not blue colored. So if we want to take a look at what the half reactions are here and who's being oxidized and who's being reduced, let's start with our zinc. We know we'll just focus for half reactions on one of our elements. So zinc's becoming zinc sulfate. So anything that's just a metal will be an element, and it's going to have an oxidation state of 0. Our sulfate has a -2 charge, and so our zinc is a +2. And we're going to see that our zinc is going to lose electrons to form that +2 charge, and so it's going to be oxidized. Our copper sulfate, on the other hand, starts as an anion. It's copper SO4, which means that if that sulfate's -2, our copper's +2. It's going to form copper metal, which will have no charge to it because it's an element. And so it really needs to gain 2 electrons to make that happen. Since it's gaining electrons, it'll be reduced. We can see pictures of what's happening in this solution. So as these copper ions are reduced, so I've got a copper ion in solution, it's becoming the copper atom that's the element, and it'll deposit on the surface of that solid zinc. And as that's happening, one of these zinc atoms that's in its elemental form will come off as it is oxidized to form a zinc +2 ion in the solution. And so the zinc atoms are becoming ions and leaving the solid, while the copper is being deposited as a solid on top of the zinc. So if we have these two half reactions occurring together, we'll see this redox reaction take place in a solid form. But if we were able to separate the two half reactions, we could take advantage of a current that would flow between the two. And that current is the electrical charge, which for us is electrons moving through a wire or ions moving through a solution. In our picture we just looked at, we were seeing electrical current as ions moving through the solution. But if we could separate them and connect them with a wire, we would be able to see that current pass and flow over a wire. And we could take advantage of that to perform perform work using electricity. It was like light a light bulb. So we need a way to connect these half reactions, and we also need a way to make sure that our charge stays balanced within them, because as ions become solids, we'll have this deficit of positively charged cations as they change into elemental forms of the material, and that would have an imbalance in our number of cations and anions in solution. So here's a voltaic cell, and this is going to show how we kind of solve these problems. So we separate the two reactions. We connect them with a wire so our electrical current can flow from one side to the other. And then we have a salt bridge that will allow us to replace the ions that are lost, so that way we always have the same charge balance. So let's break this down a little bit. So this is the same reaction we just looked at, and we said that here we go. Our zinc is going to be oxidized and our copper is going to be reduced. So coming here, we have our copper being reduced and our zinc being oxidized. So that oxidation is going to take place here on the zinc half of our electrochemical cell, and the reduction of our copper is going to take place on the copper side of our voltaic cell. And what we have is we have both the reactants and the products in the same space together. So we have this zinc reactant that is in a solution of its product, the zinc sulfate. And we have those together. But our other reactant and product, we put in an entirely separate beaker. And so we have our copper immersed in our, which is the product of the copper reaction, immersed in the reactant, which is the copper nitrate solution in this case. Sorry, it should be copper sulfate. We switched to nitrates apparently for my picture. So we have both the metal and the ion in place together, and then we connect them with a wire that electrons can flow through. And then this right here is our salt bridge. And the salt bridge is just potassium nitrate. And as we have our metal atoms form positively charged ions in solution, we would be increasing that positive charge in the beaker if we didn't have the salt bridge. But the salt bridge will allow these nitrate anions to flow into the solution to balance out that extra positive charged cation that just formed in the solution. Nitrate will flow into the solution as well to balance it out. Same thing on the other side. When we have a ion, copper plus ion, take on two electrons and form just a copper element, it'll deposit itself on that copper metal, and we'd be down a cation in our solution and have too many anions around. And so this potassium ion comes through the salt bridge into the solution to balance out that charge, so we don't have the accumulation of positive or negative charge within our beakers. And so then that creates our voltaic cell. And when we hook this wire up to those two pieces of metal, we'll see electrical current flow that we can read with like a voltmeter. And what's happening here is we have oxidation taking place, where, again, remember, oxidation is where you lose electrons. And as we lose electrons, those electrons are lost to this wire that brings them over to the copper where they're gaining electrons. It gains them over here. And we're going to call the place where oxidation happens the anode of our voltaic cell. And the place where our reduction takes place will be our cathode. And as we see this reaction take place over time through this voltaic cell setup, we will see that one of these are going to gain mass over the course of the reaction. So that oxidation is taking a solid zinc and turning it into an ion that dissolves in solution. And so we'll be having these atoms of zinc go into the solution. So this is actually going to get lighter. So the mass will decrease of our actual piece of zinc metal. And on our cathode, we're going to see that our ions are going to take, in the solution, are going to take those electrons and form the element. So they're going to become a solid copper atom on the copper electrode. And so we're going to see the mass of the cathode increase as the reaction proceeds. We have, so we don't draw a picture of a voltaic cell every time we want to talk about it. We have some notation that we use and have a format that we'll always use every time, so that way we can, as chemists love to do, delete information and consolidate it into something that someone can unpack to understand if they know the rule set. So we'll teach the rule set now. So to have our voltaic cell before, remember we had on the oxidation half, that was our anode. And on our reduction half cell, that was our cathode of our voltaic cell. And I'm going to write out what the way my voltaic cell was constructed by always putting first the electrode and then the electrolyte. So this was our electrode is the solid, which is our zinc metal. Our electrolyte that we had in solution was our zinc plus 2 ions that were floating around. And then I will have separated these with just one line right here to show that there's a difference between here's my electrode, straight line, here's my electrolyte. And that's going to take care of the anode half. We're then going to need to give information about the cathode half of our voltaic cell. And to indicate that we're switching which side of the cell we're talking about, we're going to put these 2 lines that indicate that there's a salt bridge between these 2 systems, I guess. And then we'll put information about our electrolyte for our cathode, and then our electrode for the cathode. So our electrode is that solid, so that was our copper metal, and our electrolyte was that copper plus 2 ion that was around. And so a way to kind of think of how to construct this is we start with a salt bridge, and then we put the solution, that's our electrolyte, on either side of that. A line, and then we'll put the electrode, which is typically a solid, not always. Yeah. Another way to kind of think about it is, instead of like building out from the center, is that we're piecing together on the reactant side, we had zinc, right? And copper plus 2. And on our product side, we had zinc plus 2 and our copper solid. And so they're going in that same order, but separated by that salt bridge. So we'll always make sure that the charges for our electrolytes are there. We're also going to make sure that we put in the phase, it's aqueous, and the concentration. We'll talk about the difference in concentration for voltaic cells later in our lecture series on this material. And that's a way to simplify an or a voltaic cell. Now, some of our cells will, or our electrodes will look a little different. So here's an example of something a little bit more typical, like we just talked about, where you have a metal in a solution. And so we have here magnesium metal, which usually comes kind of as a ribbon or a coil. That's in magnesium chloride solution. So it's in a magnesium plus 2 solution. But let's say we were comparing it to something happening at the cathode that wasn't a metal. A great example of this is hydrogen, where we have the reduction of 2 protons to form hydrogen gas. I can't get a like solid that I can just insert and clip a wire, like a wire to. And so we use a non-reactive electrode in this situation. And so here's an example of one that's platinum. And so you would have a platinum wire that would coil through into a solution of hydrochloric acid that would have lots of H+ ions. And as electrons flowed into your cathode, you would see those protons become H2 as they were reduced. And then you would see these little bubbles of hydrogen gas form. Other ones that are used for inert electrodes commonly are gold electrodes as well. Um, yeah. And so here, actually, let's show this. So we have, for showing in our notation, our inert electrodes. So this is on the cathode half of our notation. We have the electrolyte. And then we're going to use an extra line here to show that we have our electrode and our inert electrode. If I instead had multiple electrolytes, I would use a comma to separate them. Like if I had H plus and potassium for some reason, I would use a comma. And so we only use the lines to switch from electrolyte to electrode or electrode to inert electrode to kind of distinguish that. Here are a couple of example problems, and these will be listed again in the following page in Canvas. And give these a try, and then we'll go over the solutions together.